This year. Hi, Rebecca, and good morning, and thanks for. I think that is quite early, right? You're in California, so yeah, thanks a lot. You can start sharing your screen, probably.
Yeah.
Rebecca, we cannot hear you very well.
Yeah, I hear you very low, right? Your volume of the microphone seems to be very low. Right? But now it's better. Now it's better.
It's okay. It looks like my gain is a bit low. I don't know why it's doing it. You hear me okay now?
Yes.
Okay, it's probably just adjusting, I guess.
Yeah, perfect. Okay, so we can start actually the recording for this this last talk before the coffee break. Is the recording already on, or because we stopped the one before?
I don't think it is. I don't see anything saying recording.
Yeah, I don't see anything like so. I think that so. Minds people, can we start the recording?
It's running.
Ah, okay. Fantastic. Thanks. Sorry. Okay, so we are very happy to have Rebecca Leane with us from Slack. She's going to talk about some exciting work from last year, I guess, about gamma ray searches for dark matter in celestial bodies. So please, Rebecca, go ahead.
Great. So thanks very much for the invitation to speak today. It's a pleasure to be here with you all virtually. Thanks to the organizers for putting together this nice workshop. So today I want to tell you all about some new searches we can do for dark matter using gamma rays. So generally when we think about looking for weak scale dark matter using gamma rays, we want to use traditional indirect detection. So traditionally what this means is we just look in very dark matter dense regions, such as the center of our galaxy, globular clusters, any place where there's lots of dark matter, and we look for dark matter annihilation products or decay products. So generally we're looking in dark matter halos. So what I want to tell you about today is an alternate type of signal where we can use the gamma rays coming from dark matter annihilation, where the rates actually can be much higher than what we would expect in a halo. And particularly we want to look at gamma rays coming from different celestial objects. And the reason why I want to focus on gamma rays today is that we have a lot of excellent telescopes that already have data. So a lot of the searches proposed with celestial bodies require some telescopes that we hope to get the data from in the next maybe 5 to 10 years. But these searches, we have done them now already, and we can already report on results. So we have excellent data from Fermi, we have Hawk, and we have HESS. So we're going to want to utilize all these really excellent data sets to look for some new dark matter signals. So we already had a great overview from Joachim just now about how dark matter capture works in different stars and planets. So I'll just tell you really briefly again how this goes in not quite as much detail and explain how you get these gamma ray signals. So the general idea with stars and planets is that we have some background halo of dark matter. And dark matter can, if it's the type of dark matter that interacts with the standard model, can scatter with the surface of these objects, lose energy, and potentially become gravitationally captured. And over time, as more and more of these dark matter particles can build up, they can become very concentrated in the cores of these objects. And under the assumption that the dark matter particle is the type that annihilates, it can annihilate to some other dark sector mediators, and then we can get some standard model products. Now, the assumption for the searches I'm going to tell you about in this talk today is that these intermediate particles that are annihilating to the standard model, so like our dark mediators, either have a very long lifetime or are produced with a large boost. So if they have either a long lifetime or a large boost, if they have a decay length that exceeds the radius of the object, we can then look at the gamma rays that might appear at the surface or even further out from the surface. So the general assumption is that the boost, which is this gamma, which is the ratio of the dark matter and the mediator's mass, this is just the speed of light at tau as its lifetime, is larger than the radius of the object. So traditionally we speak about long-lived particles, but I just want to remind you it also can just be a particle that's very boosted. We'll also do it. Now, in the context of other types of searches we do with celestial objects, you can think about these long-lived or very boosted particle searches as really just being a complementary part of the parameter space. They're not necessarily really contrived sets of models that will give you this. They're just ones that have either a smaller coupling or usually a lighter mass compared to the dark matter. Because if you didn't have this, these particular conditions, what you would have instead is still some dark mediator that dark matter would have annihilated to, And if it had a short lifetime or not a large boost, instead the decay products generally, they're not neutrinos, can be absorbed by the star or the planet. And if they're absorbed, we get this heating. And instead, we just want to look at the part of the parameter space where you have lighter masses or weaker couplings. And instead, these particles just decay outside the surface. And we want to look at the gamma rays we can get from this. So that's the type I'll be focusing on in the talk today. So to actually do these searches, what sort of objects do we want to choose? There's lots of different types of stars and planets, and there's lots of different objects that are optimal detectors in different regimes. So what makes a particular object more optimal than others? So one is just its size, being the radius of the object. And generally, if you have a bigger object, you will just have more dark matter passing through the surface of the object, particularly if we're thinking about the saturation case where all the dark matter particles that pass through are captured. So thinking generally, we're going to capture more of the stuff if the object's bigger. Of course, the thing we actually want to compare to is the effective capture radius. So some things like neutron stars, for example, can be very, very small, but they might have a slightly enhanced effective capture rate just from gravitational focusing, so they can pull in lots of particles. So we want just a large effective capture radius. The other thing is, if an object's very dense, it's very easy to trap dark matter. So we just have sensitivity to weaker interaction cross sections. So dense objects are good if you want to look at a type of model that has fairly low cross sections. We also want to consider objects that have fairly low core temperatures. This generally can be ideal simply from the fact that if you have a higher temperature, you give more of a kinetic kick, so you give a thermal kick to the particles, and if that thermal kick is sufficient to overcome the gravity of the object, the dark matter particle can just escape. And if it evacuates, then we won't be looking at these annihilation signals at all, because if they've just annihilated, if they haven't been able to annihilate, we won't see anything. So generally having a cooler core temperature means we can probe lighter dark matter masses. We also want to think about where we actually put these different objects. So we care about very obviously, we care about how detectable our signal is. So for example, if we have an object very close by, this almost always wins. Simply because if you put something further away, you have a 1/r² suppression in your flux. Now there are ways to overcome this, but it's an important thing to keep in mind. We also care about, if we think about how the luminosity scales for an object, is what its size is. So if we think about the detectability, it's much easier to detect something that's larger. We're also going to consider the background that the object might have. So both the environment that we decide to put the different object in, as well as the background the object might have itself. For example, do we expect it to have gamma rays or something else in the background? All right, so the 4 different objects I'm going to tell you about in the talk today are as follows. And I'll explain to you why we want to use these particular objects. So first of all, we want to consider gamma rays coming from brown dwarfs. And the reason brown dwarfs can be really good is they're fairly big, which means the luminosity is going to be generally good if we're thinking about these signatures. They're also cold, so they have relatively low core temperatures. So if you're not used to thinking of brown dwarfs, they're kind of like what lurks between a planet and a star. So they have no nuclear fusion going on, but they're usually burning deuterium. But overall, this means it's a cooler core temperature than, say, a main sequence star. And for their size, they're quite dense. So brown dwarfs are often around Jupiter-sized, and compared to other objects that are Jupiter-sized, these are the most dense. So this means we're going to have a pretty good cross-section reach if we consider these objects. And the next candidate are neutron stars. So neutron stars are, I guess, kind of generally speaking, the classic object that's used for these type of searches. And there's a reason for this. Neutron stars are extremely dense. These are one of the densest objects we have in the universe. So this means they give us really excellent cross-section sensitivity. If you have a very weakly interacting model, neutron stars can be really great. There are some drawbacks to thinking about neutron stars. So they're very small. So if we want to think about actually the luminosity that we can detect, they're only about 10 kilometers in radius on average. So they can be hard to detect, but if we can see them, we get this great cross-section reach. And they're also fairly cold, so we can go quite low in dark matter mass. So I'm first going to tell you about these 2 candidates, because these generally might be able to give us pretty good cross-section reach. I'll tell you the second part of the talk about some searches we can do with local objects. Okay, so where can we put brown dwarfs and neutron stars if we want to look at the gamma rays that might come from them? So we don't have any neutron stars or brown dwarfs that are very close by. If we think about this really, if we think about this signal of dark matter annihilating to some long-lived or boosted particle giving you gamma rays, and you try and take the closest known neutron star or brown dwarf, you just can't see the signal. So it's below the sensitivity of our telescopes. So instead, what we want to do is put them in the galactic center. And we want to go to the galactic center because there the dark matter density is very high. So to refresh your memory, on the right-hand side, this is just a plot of a few different benchmark dark matter density profiles. We're sitting out here at about 8 kiloparsec. And if you go towards the center, the density generally is quite large. So that's good. There's lots of dark matter available to power these signatures. Also in the center of the galaxy, the dark matter velocity is quite low compared to the local position. And if it's lower, it's just easier to gravitationally focus dark matter in and capture more of it. And lastly, there are lots of neutron stars and brown dwarfs present in the center of our galaxy. So what do we want to do? We don't want to just take one of these, because if we took just one neutron star or one brown dwarf, we wouldn't see it. We can't see it in the local position. It's not going to help putting one all the way in the center of the galaxy. So instead, what we want to do is use all of the neutron stars and all of the brown dwarfs that are sitting in the center of our galaxy. And we want to stack the signal from all of these. So we're really going to integrate over every single object to give us a really bright signal that should emanate from the center of the galaxy. And this will give us an indirect detection flux from the galactic center that comes from celestial objects. So let me just explain a little bit more about how you can think about this signal and how it compares to the traditional dark matter halo annihilation. So if we think about how the annihilation rate scales in the center of our galaxy, this is fairly trivial. It's just classically the thermal average of our annihilation cross-section times the number density squared of the dark matter. So clearly it goes like number density squared. You just have two particles participating in this annihilation process. So how does it look instead for this celestial body focus scenario? So this galactic center population signal powering something at the center of the galaxy. So there are a few steps to see how the annihilation rate scales. So let me just quickly walk you through how this works. So we think about the maximum capture rate that you can have for dark matter particles passing through these objects for just one singular celestial body. It just goes like a circle of the area of the object. So it's a circle and not a sphere, because you can think about, it's really just like the total effective area the dark matter particles can pass through. And this is multiplied by the dark matter number density. So of course, if you have more dark matter particles available, this rate will increase. And then we have a velocity factor for the capture. And this is our gravitational focusing term. So you can see that the gravitational focusing goes like the escape velocity squared. So the escape velocity is directly related to really how dense this object is, so how good it is at pulling particles in. We also have the halo dispersion on the denominator here. So if you have a lower dark matter velocity, you can clearly see this term will increase. So we have more gravitational focusing, so it's easier to pull the particles in. And we have this xi factor on the edge, and this is just taking into account the relative motion of the object in question with the halo. Okay, so we can plug in numbers for all of that. And if we think about the population capture rate, we want to just then integrate over all the neutron stars and all the brown dwarfs that we model. So we're looking at the total capture rate coming from a volume that covers all through the center of the galaxy. Then if we assume that annihilation and capture are in equilibrium, which generally will be the case for most models of interest that we care about, we really just say then that the annihilation rate of the dark matter particles is equal to the capture rate. And we can have an extra factor of 2 depending if you have Majorana or Dirac particles. So if these are directly related, then we can clearly see that the annihilation rate for this process won't scale like the dark matter density squared. Instead, it will scale like 1 power of the number density. So that's coming directly from the capture rate we see here, with the assumption that it's in equilibrium. And then this is multiplied by the brown dwarf or the neutron star number density, just coming from integrating over the full population. So compared to the halo annihilation, this scales very differently. And this can be really important depending on what type of particle model you have. It can be that using this full population of different objects in our galaxy is a better way to do indirect detection rather than the standard sort of halo annihilation. So I'll just compare a little bit more so you can see why this is true. So firstly, as I said, you'll get a different signal morphology. So in principle, you could do studies to look at what you would expect for the annihilation rate in the center of the galaxy, which would be interesting. We didn't do any of that in detail, but we should see a dark matter density squared versus a dark matter density 1 power and 1 power of the stellar density, which is kind of cool. But importantly, what you can see, and this will matter for different types of models, that this like focused annihilation rate can be focused above the Halo levels. So this plot on the right-hand side is showing you the total annihilation rate within 100 parsecs. So we're just choosing some volume to directly compare what the rates are. You could pick a different volume if you felt like it. And for the, on the x-axis, we have the dark matter mass. So if we just had S-wave annihilation, so this is the classic no velocity suppression in our annihilation rate. So just say for a standard WIMP, for example, we would see that as we go up in dark matter mass, this should decrease. So this is just because if you have heavier dark matter particles, you'll have fewer of them around. In comparison, we see for this, if we use the brown dwarfs, the particular annihilation rate we expect to see isn't dropping off with larger masses. So we can have quite large rates. If we compare to S-wave, we'll only do better if we have quite heavier masses with the brown dwarfs. But if you had a particle physics model that only had P-wave annihilation, so this is if you do an expansion in the velocity of the annihilation rate, this can be really suppressed. So at the moment, our classical indirect detection experiments are only sensitive to annihilation rates that are around S-wave. Even then, we can't probe S-wave annihilation for all dark matter masses. Typically, it's for lighter dark matter masses that we can do this. But you would see here in this case, you have a better way to actually try and detect the annihilation that you would have if you have a P-wave rate, which is quite interesting. All right, so it's one thing to say that these rates are higher than what you might expect in the traditional scenario, but how does this actually compare to what we can detect right now with our telescopes? So we have to compare with known gamma ray data that we have. So what we can do is we can use Fermi data and the Hess data for the galactic center. So this plot on the right is showing you the flux that Fermi has measured. So the left-hand side here is the maximum flux, and the x-axis is the dark matter mass. So we're relating what Fermi has measured to the dark matter mass by just taking a one-to-one correspondence. So we're assuming that we're effectively taking dark matter mass equals the photon energy to show these lines here. But you can see that Fermi has detected something. So this is kind of higher and is dropping off. This here actually is the galactic center excess. So we already have a big signal of gamma rays coming from the center of the galaxy, and we don't know what it is. So we're not going to try and explain that in this setup. It turns out actually you can, which was very surprising and a bit amusing. That's not the main goal of what we actually want to do. So we'll see just how well we can otherwise detect these signals over the gamma rays that have already been detected. So if we take these, the brown dwarfs, if we take different density profiles, so this is for 1.5 using brown dwarfs, but so this is just for a profile that's a bit more cuspy, like spiky. And this is for brown dwarfs with just the standard NFW, so kind of spiky, but less spiky than this choice up here. So we see that the fluxes we expect from the brown dwarfs are definitely above the sensitivity of what we've already detected. So these are really quite bright signals. If we look at the neutron stars, they're not as easy to see. So if we have a very cuspy profile, we can see them using Hess. If we have just a standard NFW, this is pretty difficult to see. You can see a little bit of something at higher masses, but otherwise it's going to be below what we've seen already. So the assumption in actually showing these lines is, first of all, that the dark matter particles are not annihilating directly to gamma rays. So you actually can go, of course, in particular models to lots of different final states. Just to show you how some limits could look, what the sensitivity is, we're showing direct to gamma rays. So to be clear, this means you will get, this is the best possible reach you would have for this search. Because if you go directly into gamma rays, a lot of the energy is really focused around the dark matter mass. Otherwise, we don't have any model assumptions in this scenario, other than the scenario, other than the condition that the mediator must escape the object in question. Okay, So given this signal is so much larger than what we see with our telescopes, we can set some constraints. So this is what the constraints look like. We find that for brown dwarfs, we can actually fill in a lot of parameter space with the assumption that you annihilate to a long-lived particle or very boosted particle in the sub-GeV mass range. So compared to direct detection, we have a good few orders of magnitude here in comparison. This also, of course, does have the assumption that you have an NFW profile. We don't actually know what the density profile is in the center of the galaxy. It could be something that's a little bit more chord. And if it's chord, the limit here would weaken further. So we don't know what the profile is, so we just show you two different values of the gamma here. So very cuspy, slightly less cuspy. So we can do well with the brown dwarfs in this light mass range. We don't have neutron star limits in this mass range. As you might recall from the previous plot, the neutron star flux just wasn't large enough to see over the already galactic center excess that we have. So we can't do anything there. But if we go up to higher masses, the neutron stars actually might be able to do something. But the sensitivity is only when you have this really cuspy profile. And again, we don't know what the profile is. This is also really about the maximum value you would want to take for these sort of profiles. So if this isn't realized, you won't actually see the limits here. And then it might be surprising that it seems like the sensitivity is really to quite low cross sections. So why does it only kind of just creep in? Why can you only just see this and only in this threshold? So one important thing to take, or something to keep in mind when you have these limits is if you want to think about how much dark matter the neutron star can actually capture. So we want to think about really what the saturation scenario is, where all the dark matter that passes through a neutron star is captured. That corresponds to a cross section of around 10 to the minus 45 or higher. So if you try and increase your cross section, say to 10 to the minus 43 or 10 to the minus 41, the same amount of dark matter is captured. So even if, because they're just so dense. So even if you think, oh, if I put a higher interaction rate, I get more of it there is a threshold where just increasing your interaction strength doesn't help you because you already captured everything. And for neutron stars, because that already is roughly here, this bound looks like it's really powerful, but it's actually only just scraping in. So you can go a little bit below this saturation of around 10 to the minus 45, but not very much. So the neutron stars can do something maybe at heavier masses, but it seems like the most promising really is the fact that these brown dwarfs can be so bright that you can see them above the galactic center excess even, to have quite strong new limits. An important thing to keep, to also keep in mind with this plot is that really there are a few assumptions that go into making all the limits that you see here, but they're being directly compared. So if we think about direct detection, there's no requirement for dark matter to annihilate to set those limits. So we're just comparing directly the scattering cross-section in that case. But also for these different objects, they have different sizes. So there is also the case that, neutron stars are really small. The sun is pretty big. So if we're imposing the condition that the decay length of these mediators has to just exceed the radius of the object, if you had an intermediate decay length, you might actually be absorbed in one of these objects, such as the sun, but then escape in the case of neutron stars. So you should keep in mind that some of these limits can appear or disappear depending on what part of the parameter space you actually are in terms of the particle physics model. Okay, right. So now I want to tell you about what we can do with local searches using gamma rays. So it seems like using brown dwarfs and neutron stars, we can get into a good bit of the parameter space using these gamma rays, but things that are close by are always going to do better. So things in our solar system, just from the 1 on R squared, are always going to give us really excellent limits if we can actually access them. So this is why typically the sun has been used for almost everything, looking at dark matter annihilating in different stars and planets. The sun is huge. We see it in the sky. It's very close by. And the great thing about the sun is we have looked at this in a lot of detail. So we've looked at it with Fermi, we've looked at it with Hawk, which is a water Cherenkov telescope. So that's great. So we'll be able to actually say something about that. The limitations of thinking about the sun, and only one way you can try and win over the sun, is that the sun is quite hot. And because it's quite hot, this means that it actually has a higher dark matter evaporation. So what I mean by that is just that the dark matter particles that are trying to settle into the core are getting a pretty solid thermal kick. And it means that then you will evaporate dark matter particles around a few GeV approximately from the sun. So we can't access lighter dark matter masses with the sun. But lots of other limits we have, so lots of other benefits. It's really huge, it's close by, and we have excellent data. So making the most of all these different features, a few years ago, I actually looked at this in some detail, and we set very strong constraints using Fermi and also working together with the Hawk collaboration. We actually did this search and saw nothing and put some very strong limits. So you see, comparing to, this was the direct detection limit at the time. This is just spin independent, I should emphasize, simply because if you take the spin dependent, we take the spin independent, you would instead by now see something that's much further down in the parameter space. So Hawk can still overpower even spin independent, where this cross section will be much further down, particularly at higher masses. But if you had models that were spin dependent, you have many orders of magnitude stronger probe that you can get using the sun. So this was already done a few years ago. So now what I want to tell you about is a new search I did with Tim Linden, and this is using Jupiter. So why would you want to use Jupiter? So for the sun, we have these really strong limits, and the sun generally is going to do better. It's closer, it's bigger. But the main benefit you get from thinking about Jupiter is that it's cooler than the sun. So the core is giving these dark matter particles less of a thermal kick, which means we should have some MeV scale dark matter mass sensitivity if we consider Jupiter. So really what we should be able to do is have some sensitivity to the left of these curves. But then we looked up Jupiter and gamma rays, thought, okay, this should be fairly trivial. There'll be already some fluxes that are measured, and we can just, apply a formalism and just probably set some limits. But instead, what happened was when we tried to look this up, turned out nobody ever looked at Jupiter and gamma rays in history. So there was nothing to compare to. This was really surprising, given, we've known about Jupiter for many millennia, and I guess no one knew what Jupiter looked like in gamma rays. So it seemed really exciting in the sense that we could be the first people to do a measurement of Jupiter in gamma rays, but also we could learn something new about Jupiter. You could imagine, what is the probability you find a dark matter signal this way? Well, maybe it happens, but maybe it doesn't. And if it doesn't, there's lots of other things that we can learn. So just to be clear, if we find gamma rays doing this search, they could come from things like acceleration of cosmic rays in the Jovian magnetic fields, or they could come from interaction of the cosmic rays with Jupiter's atmosphere. So this could tell us potentially something about Jupiter's astrophysical properties, maybe that we didn't know before. And of course, it could be something a bit more exotic, so a new dark matter signal. So to do this, we did the first Fermi analysis of Jupiter. And just to give you a bit of information about exactly what we did, so we took 12 years of the Fermi data. So this is roughly as long as Fermi had been running. And we're looking at energies between 10 MeV and 10 GeV. So if anyone who's thought about Fermi data before, going down to 10 MeV is very low. So this is pushing Fermi to its limits. As far as we're aware, nobody actually ever did a steady state analysis using Fermi data below 100 MeV. So this is going down very, very low. This is also where Fermi's performance will be degrading, but we want to go as low as possible just because this is a region of interest for our search. So we're going to see what we can do. And to do the analysis, we also had to think about how do you actually set this up? And what we did, we thought about the fact that Jupiter goes around in the sky once every 12 years, 12 Earth years. So that's it's 1 year is 12 years to us. So this means that if we have 12 years of data, it's going to just go through the sky once in its coordinate system. So what we wanted to do, so Fermi has mostly all sky field of view. At a given time, it can see about 20% of the sky, but give it a few hours, it will see everything. So Fermi is looking for a good fraction of the time at every place Jupiter will go across the sky. So what we want to do is select all the photons that are within Jupiter's orbit. So not just when Jupiter's there, we want to look at gamma rays that come from every position within 45 degrees of where Jupiter will go during its orbit, because we want to build up a background model. So we'll keep looking through this whole orbit for the whole 12 years, whenever Fermi can see this region. And we'll build up a data-driven background model for when Jupiter isn't there. And when Jupiter actually does move into a particular part of the orbit, that will be considered like our on region. So once it's on, okay, we take, we collect the data, what do the gamma rays look like within this 45 degrees? And if it moves out of that region, that's an off region. So it's not there, we keep looking, that can be part of the background. And in part of doing this, one difficulty is that compared to other analysis, like looking at the sun in gamma rays, the sun is quite bright, so it generally overpowers everything else that we would want to look at. But also, if we only have one orbit through the 12-year data period that we have, if there's a really bright flare that happens to very unfortunately go off at the wrong time, there's not much we can do about it. So for the sun, instead, there are lots of flares you will see just happening in the background, but because the sun over the 12 years is moving through its coordinate system many times relative to us, we can usually kind of account for these. So instead, what we have to do, what we choose to do, is just mask all these things. So as soon as we look in the Fermi, the catalog of all the flares that are kind of known to have happened, we observe them in the data when we go looking there, and we just mask them out. So we mask out all the flares. We're going to lose some of our data from doing this, but we don't lose too much. We only lose something like 15 to 20% of our data. So we still have otherwise 12 years, which is pretty good. And we also then just mask the sun and the moon, because these are also bright objects that are appearing in our coordinate system, and we just don't want to deal with them. We could model them, we just choose to just block them out. So once we've done all of that, we then have these on and off maps. So on being the part of the sky when Jupiter was there within 45 degrees, and the off map events are all the events from looking through this path when Jupiter wasn't there. And if we subtract these, we should then see, is there some residual or not in the Jupiter position? So what do we see? The left-hand side here is showing you the counts map. So this is like the on region when Jupiter is there. Now, the size of Jupiter in this map, so this is just the Jupiter-centric latitude and longitude on the X and Y axis, so 45 degrees. Jupiter at these energies, so we're showing you one energy bin, 1 to 3 GeV, is like a dot. So it's about a degree at these energies. So it's roughly this position. All these other things you see in the picture are just other things in the background that we haven't masked out. So a bunch of them are really just other flares that happen to be going as we're looking. So it should be in here. So the counts map by eye, we don't seem to see anything lighting up. Here is our background map. If we then just subtract from these, this is our residual. So if Jupiter was emitting in gamma rays, we would see something very bright lighting up here. Instead, we see nothing. So we actually see no statistically significant emission associated with Jupiter. So that's interesting. It looks like Jupiter isn't emitting in gamma rays, at least within Fermi's detection threshold. But if there's nothing there, we can use this to set the first limits on the Jupiter flux. So this is the measurement that we actually do. So mostly we see nothing statistically significant. So this is the energy and this is flux here. So we do actually, so these are the measurements that we have. The error bars are only statistical, it's not systematics, and a lot of these bins are actually highly correlated. So we do see like a really tiny excess of like 1.5 sigma. Excess, I shouldn't even say excess, 1.5 sigma is not an excess, you expect this to happen. So we don't see anything that looks too surprising. If you actually zoom in on the really low energy bins, there is something, depending on how you actually, how wide you make your bins, there is potentially something here, there. So the case I'm showing here are very wide bins. And if you have these really wide bins, if you zoom in on this region, you see this thing on the right-hand side here, and there's nothing statistically significant. So we see that with these error bars, looks like we're pretty much consistent with 0. So I should say this blue line here is just 0. But depending how we think about this or do this, sometimes we actually do see something kind of happening on this bottom end here. But what I should really emphasize is going to these really low energies, it's really hard to know how the systematics should work with Fermi. Nobody even studied Fermi data in this regime, in steady state regime. So there is maybe something going on at the lower energies, but overall we just say nothing we think you should take too seriously. Though it would be really interesting to see what would happen if you did analysis like this and extended it to the lower energies, particularly with potential upcoming telescopes, so MEGO and EASTROGAM. So these are designed to detect things at MeV, gamma rays at MeV energies, not like Fermi where we're kind of pushing pretty far away in this case. All right, so what limit do these correspond to for Jupiter? So if you want to set limits, the total flux, which is this left-hand side here, just goes like the annihilation rate and then 4 pi r squared, where this, well, this is d, so distance to Earth, is what goes in here. And this is then multiplied by the gamma ray spectrum that you have. So the assumption on the plot on the right-hand side, again, we're just going to go straight into gamma rays for simplicity. But of course, for different models, you could have different final states and the limits would look different. And then we have the branching fraction of the mediator to the standard model final states, and then some survival probability factor. So if we plug these things in and compare the direct detection limits to what we can do with Jupiter, we can get potentially a number of orders of magnitude stronger sensitivity. But again, there are assumptions that go in these limits, and I should really emphasize there are assumptions. So you shouldn't look at this plot and think these are the cross-section limits that are just generically going to hold for all cases, because they won't. So first of all, the limits that we're showing here assume you have direct theta gamma rays. Again, if you had other final states, they wouldn't detect, you wouldn't have sensitivity such low cross-sections, simply because the gamma ray spectrum is very peaky. And if you put that in here, that will actually give you the best sensitivity. So for example, if you chose electrons instead, you'd probably be sitting up by a few orders of magnitude. We also have assumed that the mediated decay length is larger than the Jupiter radius. This is not generically going to be true. It will correspond to a number of different models, but you just need to keep that in mind comparing to other limits that are there. We're also assuming that we're in equilibrium. And depending on your model, this might not necessarily be true, particularly all the way down to these very low cross sections. So the way you should think about the limits that are shown here are really, this is the maximum sort of parameter space you should be able to probe in the most optimal scenario. If you apply this to some particular particle physics model, you might find instead you sit somewhere in the middle. But the overall point of showing the limits this way is, first of all, we have to show you something to try and compare to show how strong the limits could be. But it particularly want to point out that it seems like if you can really gain something like nearly 10 orders of magnitude in the best case scenario, probably when you actually apply this to another class of models that aren't as optimal, you might have 10 orders of magnitude, but you probably still get something. So it's worth looking at this in some more detail to see how this might map onto specific particle physics models. We also show here for comparison this brown dwarf galactic center search, the one I was telling you about earlier. So this line here is assuming just an NFW profile. So we see that with Jupiter, you can go further down. And this is the fact we use brown dwarfs, which are more dense than Jupiter and many more of them. This is just the 1 over r squared. So this really highlights how much you win from using something very close by. So Jupiter is really excellent in that regard. Okay. Okay, good. So to summarize what I was telling you about today, so I was discussing some new gamma ray searches we can do for dark matter in celestial bodies, particularly getting some good sensitivity to much lighter dark matter than traditionally we would with other searches. So I discussed at the beginning a search for gamma rays powered by the galactic center population of either brown dwarfs or neutron stars. And using the brown dwarfs, we could get very good limits, particularly at light masses. The neutron stars can be quite sensitive to smaller cross sections for higher dark matter masses. And the interesting thing in this case is that if you want to think about the range of models and how we probe them, so using classical indirect detection, just looking at the halo, or instead thinking about a full population of celestial objects that can give you a really large gamma ray flux from the center of the galaxy, you might be able to probe your favorite model using these celestial objects rather than the Halo Annihilation, particularly if you had, say, a P-wave suppressed model, or you wanted to look at something at higher dark matter mass, where generically indirect detection doesn't do as well. So it's really a different way to think about how we can get indirect detection signals. And the morphology of this signal will also look very different compared to standard Halo Annihilation. I also told you about new searches we could do for gamma rays in the local position. So briefly about the sun, which is a classic thing people have thought about for a long time, but also in particular what we could do with Jupiter. So we did the first analysis of Jupiter in gamma rays and found that it can be really sensitive to these classes of dark matter models where you have dark matter annihilating to a long-lived or very boosted particle and giving you gamma rays. Interestingly, it was the first search of Jupiter, but first search of Jupiter in gamma rays, we didn't see any gamma rays. It doesn't look like Jupiter is emitting anything there. But it does motivate follow-up searches with MEV gamma ray telescopes such as Omega or Eastergam. They're going to do a much better of looking properly at the MEV gamma ray range compared to Fermi, which is really just not optimized for this. But overall, I've showed you that celestial objects can be a really great way to think about looking for weak scale particles in gamma rays that is very different to our traditional indirect detection. So we can look for dark matter annihilation in these objects, and we might actually be able to use these as the superior probe of some of these different classes of models. So that's all I wanted to say. Thanks for your attention. Thanks
a lot, Rebecca, for this very, very nice talk, and it actually fit the workshop perfectly, about stars and fundamental physics. So we have, of course, time for questions. Eduardo has his hand raised, so Eduardo, go ahead.
It's a very good question. So first of all, thanks again for the nice talk. Do you have any plot to show with projections for MEV telescopes like Astrogam or something like this?
Yeah, so I don't have one in backup at all. So you're wondering what you could do for Jupiter, for example, or you mean just in general? What is this?
With Jupiter.
Yeah. So yeah, no, sorry, I don't have an estimate for that.
Because obviously, it also depends on the kind of telescope, what's your field of view and all these kind of things, of course. But I was wondering if no, I will have a second question, but first, Andrea, I think you have questions.
Yeah. So yeah, so I don't have a plot already because we didn't do a projection with that. But I would think, part of it is if we believe the limits that we have in this range, so I think it would be a question of really what probably happens, particularly in this green, really below 0.1 GeV, how this really should look here. Because it could be, if you do this with an MEV gamma ray telescope that's made for this, these limits just look very different. So you could say, okay, maybe they actually see something. We see something maybe looking a bit fishy going up here, but this also probably is just systematics. But maybe they see something and that would be very interesting. If they don't, and then they just have a zero flux, they should be better than Fermi by, I would think, a few orders of magnitude if we were looking in this region here. The other thing though, so we didn't show the limits, but if you think about, if you start going too far to the left-hand side, you just don't have dark matter in Jupiter anymore. So you have to think about when dark matter evaporates. And for different classes of models, you won't even necessarily saturate this line. So it is somewhat model dependent. But yeah, we could have put a projection on here. I think you would likely do even better in this regime. But yeah, if you go too far to the side as well, the dark matter is just not in Jupiter anymore. It's a separate
point. That actually takes me to the follow-up question. So I understand that, of course, if you have a very clear signal, of course, it's a discovery, clearly. But the point is that, how much do we know about the background looking at Jupiter, for example? So how do you know that what you're seeing is dark matter and not, I don't know, something coming simply from the atmosphere or some...
Yeah, for example, this is also my question, because I may imagine to have, for example, cosmic ray acceleration within the atmosphere, right? So that would be a background that you may model, right?
Great. Yeah, great questions, great points. So first of all, we didn't know how much this actually would be happening in Jupiter. So if we had a very clear detection somewhere, you see something really coming up very high where there's an obvious excess, we wouldn't know for sure what that was. So what you would do in that case, if we actually had a very clear excess, is you can just find what is the best fit. So you can fit different spectral shapes to this. So for example, if we were thinking about the dark matter scenario where it's going directly to gamma rays, you get a very spiky sort of spectrum. And this is generally what you would do with any search. In general, you would think about what is the signal shape you expect and any potential backgrounds. And in this case, looks like the background's nothing. So if we had a big excess, it'd be, okay, what is that? And you'd have different hypotheses. So you could do, if you were thinking about cosmic rays interacting with the atmosphere, giving you gamma rays, there's a characteristic sort of shape you would probably expect. And you could do a chi-squared for that and see what hypothesis seemed to be best. Is one way that you would be able to disentangle the two. But there's probably a number of things you would have to do. If it turned out, for example, for the dark matter model, that seemed like that was the best shape, you still wouldn't know if you actually had discovered dark matter, because of course it's possible somehow something else happened and it didn't have the spectral shape we expected. You would never believe for sure we actually found dark matter. But this would be, as we would do with any other experiment, we would then look in a targeted way for a consistent signal in other places, particularly if we got a particle physics model could explain it, we just look for that same particle model elsewhere and see if we saw something consistent.
The point is that, like, obviously in the laboratory and in the other case, you can try to understand what's your systematic. Here, it looks like we really don't know what kind of systematic you would expect from Jupiter, like even in terms of spectral shape. Like, for example, it doesn't look like we know what kind of background we expect. So actually, even understanding the background, like the background, it will be a first signal. Even detecting the background will tell you something. As you were pointing out, that's interesting because you can learn something in terms of gamma rays from Jupiter. The problem is that then you have to understand the background. That was just
for sure. Totally agree. But I think so. This happened with other objects too. So there's like the sun and the moon emitting gamma rays. And I think the moon is not so surprising. So for the moon, if you look at the shape of the gamma ray spectrum that Fermi has detected, it looks like it's just from cosmic rays interacting with like the lunar regolith, and then that's why you get the gamma rays, and that seems to be okay. But I think people didn't necessarily expect it to be as high as it was, and particularly for the sun. So the sun emits in gamma rays, and this is extremely surprising. And we don't actually know for sure why that is yet. So there is a source of gamma rays up to around a few hundred GeV coming from the sun. So when we looked at these solar limits before, we said, okay, we can just demand that if you want to set a constraint, the flux is much larger than what you observe. That's always conservative. Yes. But then the question is why? So it'd be the same for Jupiter. If we saw something and we didn't really know for sure what that was, and it wasn't that, the best explanation, for example, was something very sharply peaked, which you could say maybe likely was dark matter and not some other background, when you generally expect more of a continuum sort of spectrum. But I think that would then spark a lot of astrophysical studies as to what do we expect, what could that be? And you would need to investigate that. So I totally agree. If we saw some bump, I would not just say we've got dark matter, that's it. I would say, we need to look into what all these possibilities are now. And because people have some level of experience thinking about what happens with cosmic rays in atmospheres of objects, we could start by thinking about what have we learned so far, what might we vaguely sort of expect, but probably would have to research this in a lot more detail.
Yeah. Thank you so much. Thanks for the answer.
Yeah, thanks for the
I have
questions.
another quick question. If there is, we have done, we are in the break. So probably you just say that, but I missed it. So in your plot, you have a sharp cutoff in the mass, right? That is typically, yes, for example, here when you look at Jupiter and Sun, right, in the mass there is a sharp cutoff. It's typically not non-physical. It's just because you just impose the evaporation, kinetic temperature smaller than some binding energy.
Yeah, exactly. And that is not generically actually what you would expect for a particle model. So there's two things. One, you can also see this with the sun with these limits we've done earlier. So actually people did calculate this in some level of detail just for WIMPs. And instead what you really expect is if you go up in cross section, generally then you actually can trap a little bit more and it will go a little bit to the side. So this, when we had done the sun and cut at 4 GeV, this is fairly conservative, but realistically that actually goes to maybe 2 GeV if you go to really high cross section, something like that. And then for Jupiter, it's a similar thing. So we've just said, okay, this is the condition that we impose. And particularly if you have long range forces, we expect for sure you should be able to saturate this line. But for WIMPs, you won't, particularly at these lower cross sections, be sitting here. You'll actually be sitting more kind of in this region up here. but that depends on the model you have. And I think a big part of what when we show these limits, we didn't want to too much go into all the different particle physics possibilities.
Yeah, sure.
So that's something that we're looking at now to really see, okay, if you want to think about a specific model, what does this mean? So instead, yeah, you should just think about this as kind of the maximum space we think you realistically could be probing. But I totally agree. If you do a full thing, you don't see a straight line.
Okay, perfect. Okay, thanks a lot. So I don't see any other questions. So I think that we can thanks Rebecca again and stop recording.